So, like Tim said, yesterday you learned a lot about the Condor and how to do stuff locally, and today we'll try to go beyond that and go truly distributed computing. And you will see it's not that different. But let's go through the lecture first, and then after that we have exercises, and you will see what I mean with that. So let me just introduce myself. So I know you've seen me around yesterday a little bit, even a few have talked to me, but just so you have a feel who you're talking about, and it's not just somebody that started yesterday. I have been working with distributed computing since '96. Yes, I'm old. Working with grids since about 2005. I have leading the OSG gliding factory ops since 2009, and you'll see what glidings are. And we have been deeply involved with the development of the override systems in many ways. But I have mostly worked with physics communities, high-end physics, like CMS, CDF, Chloe. Although I have worked with other scientists, but I don't really know much about anything but high-end physics in computing. So, just a reminder that if you have any questions, ask. It's fine to do it during the lecture, during the demo, during the exercise, during the breaks, whenever you feel like. If I don't know the answer, I'll find somebody who likely knows. If he doesn't, he'll find the next one. We'll find somebody to answer the questions anyhow. So don't be shy. Ask. You're here to learn, and we're here to teach you. So that's the idea. So, just a small reminder what we're talking about. We're talking about high throughput computing, right? We are, if you hear others talk about high throughput computing, you usually hear them called batch system computing. This is because you submit jobs and you wait to get them back. And the whole paradigm is about emphasizing the maximum useful computation you can get out of a fixed number of resources. Or at least, this is what the resource providers feel about. It's high throughput computing because we want to get as much useful computing out of this cluster we are managing. And we are doing batch computing because that's the way to get it done. But really, this is from how source owners see it. But really, from the user point of view, you don't care about that cluster. If it was idle all the time, you would not care, apart from the fact that you want to get as much computation done for your own purposes. And you usually have a fixed deadline where you have to do it. Now, that's at least how you should think about high throughput computing. And I must admit that we are still not doing a good job of having enough people think about it. So it's not, oh, I have to do these 3 computations and then I go away. You should think, okay, I'm likely to get 1,000 CPUs for the next 6 months. What could I use them for? If I get another 1,000, what else could I do? Can I do more computation? If I do more computation, can I get better results? You should start to think in those terms. Not, oh, I have this problem, will I be able to get the CPUs? No. If I get X amount of CPU, what I can do, if I get twice as much, can I do more? If I get 10,000 more, can I do even more? That is big. And in the HTC that you have seen yesterday in a dedicated environment, the amount of resources available is just the upper bound. You will almost never get all of them. You will get a fraction of them. But that's just detail. You still want to get as much computation done by the deadline you have, and you should schedule your, define your problem in such a way that if you get 80% of what you meant to compute by the deadline, it should still be able to do something. And the last 20%, or even just 20% and 80%, you want to get as much as you can in before the deadline, then use it. And try to push for more if that gives you useful results at the end. Now, this lecture is so-called distributed high throughput computing. And you may wonder, what isn't high throughput computing already distributed? It is. But when we call distributed, we mean really distributed, going beyond a single cluster and expand to a global scale. So getting as many computer resources from anywhere where you can get your hands on, not just your local cluster. So from the user point of view, a DHTC is really just a HTC which has way more resources, but on the other hand, it's slightly more heterogeneous. You don't have just your local cluster that you know how to talk to the sysadmin and get it configured the way you want. If you really want to go big, you will go to places where you don't know anybody that can help you. It's very unlikely to have a shared file system, so you would have to deal with it. And the compute nodes are likely far away network-wise. So network will be slow, high latency, and all the problems that come with it. And for some the DHTC systems, you may not even know how many resources you have available. So you don't have really an upper bound. You don't even have the average. You just know there's a bunch of resources out there, and you have essentially explored how much you can actually get out of them. Now, we have a whole day tomorrow to deal with this part. How do you live in a system that doesn't have a shared file system and has a compute nodes that are far away network-wise? And Derek will explain you what you can do, tips and tricks, and what can go wrong. Today, we will still, in the exercises, we will have to be aware of it, but we'll take the easiest possible route in order to get around it. So, said that, if you have really listened to what I said, you see that DHTC and HTC really is not that difficult. It's just that different. It's just a batch system with more resources. So why do we have a lecture on it in the end? From you, I really should not make it a lot of difference. The reason we have a lecture here is that we will have some hands-on lectures, some hands-on exercises on DHTC today. You will actually use resources that are not in Wisconsin. So getting some details is useful. And I expect several of you will not be just dumb users. You may actually get involved into either managing, developing, helping with distributed high throughput computing system. So knowing how it works, it's useful. But even if you are, no offense intended, a dumb user, just being able to do the exercise is useful. So, in a nutshell, a distributed high throughput computing system is just a computing HTC that has clusters in many places. That's it. From a user point of view, that's all you want to care about. You submit jobs somewhere, and they get spread around in as many places as they can be. You may ask, why do we need to spread resources around? Why can't we just put everything together? To a certain degree, you're right, because putting everything in a single place is the most efficient thing you can do. You get away, you can configure them all the same, you can make a shared file system, no network print problems, economies of scale, everything. But life is complicated. There are practical reasons why you cannot do that. Your computing center just cannot support more than a certain amount of CPU. It takes cooling, power, it takes cooling, it takes manpower, you just cannot afford it. It's political. You may not get the money to put it there, but if you ask it to get it there, you will get it. Never underestimate the power of politics. It's everywhere. It may be, there are economical reasons. So yes, you may have a small cluster in your basement and you're happy with it, but if you want to expand it 10 times as much, it's probably cheaper to buy it from somebody else. And they are hosting it because they have economies of scale, they are good at doing it. You may be good at managing your 10 machines, but when you go to thousands, it's probably not cost effective. And there are opportunistic reasons. So somebody in the building across the street has a cluster that they have built big for whatever reason, and now it's sitting idle doing nothing. So if you can get your hands on that machines for the next 2 weeks because they're not using it, well, that's a lot of CPU. So these are all reasons that I'm not saying it's comprehensive, but these are the main reasons why we want to go with distributed high throughput computing and not just your dedicated cluster in the basement or in your computing bureau. Now, as a corollary though, each of the various clusters has a different owner. And they bought it, they operate it, they decide how it looks like and how they will manage it. Which means it is very unlikely that it will be managed by a single scheduler. So this picture is really an idealized one. You will never get it in the real world. Why? Well, you have local user, local policies. So whoever bought the cluster bought it for their own users, and they want to make it look and feel the way local users like it. You come in from the outside, you are a second-class citizen, so they will not change everything just so that it will please you. And if you go to different places, different users, different administrators. And that implies, this is due to the fact that they have existing infrastructure when you come in. They have built it before you came. They will have different technological preferences. I think Tim mentioned yesterday that Condor is just one of the many bed systems around. You have Condor, PBS, LSF, SGE, Slurm, and you can write your own if you really want to. So they all have benefits and negative points. We like Condor, but I would never say it's the best in the world. It's good for a lot of things, but it has problems. So people like other ones, and I fully sympathize with them. Also, since they are distributed in different places, you don't want to have a central scheduler that when your local networking goes off, your cluster is also dead. You may still do a lot of useful computation even if your campus is isolated from the internet. So you want to make local scheduling decisions locally. And then there is again money, policies, politics, and everything that I said before. So how do we move on? Users still want that idealist picture, right? We want a single place to submit, and it should go anywhere. You don't care less where the resources are coming, as long as your computation is being done, right? So what we will end up with in the DHTC world is we essentially stitch together the resources with least resources. So while the whole cluster is managed by different people, we will just lease some of this and make them in a pool that is managed by this one. So essentially, in the end, what we end up is with a system that knows only about the least resources and the fact that they are distributed around the world and managed by different people becomes sort of a non-issue. And we call this an overlay system. And it's an overlay because it's really a bad system across resources that are managed by others. So think about the layer on top of existing computing infrastructure. So from your point of view, as a user, you really see nothing different than before. A scheduler and a bunch of resources behind it. But because they're leased, they may come and go much more faster. It's not a fixed amount, but I can lease more because I need more, and I terminate the lease and return it to the owners whenever I want. Of course, you still have all the drawbacks of the DHTC, which means no shared file system, or at least it is more heterogeneous. You definitely have wide array network. You can do something about heterogeneity, and you could potentially create a shared file system, but you are running on a wide array network, so that's a big problem. You cannot beat the speed of light. If you are 2 different coasts in the US, that's about 100 milliseconds round trip time. If you know anything about networking, you know that's a bad thing. Now, we said we are leasing resources, right? So somebody needs to do the leasing. It doesn't just happen magically out of the thin air. And definitely you cannot count on whoever runs the machines to do the leasing for you, because you're coming from the outside and leasing them from them. Yes, they will be happy to lease it to you, but somebody has to come and say, I want to lease it and attach it to the schedule. And a corollary of this is that once we start creating overlay systems, well, you probably will have more than one. So we will have different schedulers that are leasing different parts of the various classes that are around. So I just color coded them, so sort of easy to follow. But really what is happening is that now we have different people running the machines, and we have different schedulers, different managing different subsystems of those machines around. And you can think that this is managed by biologists, this is by physicists, this is computer scientists, and these are the local users that are left with just two CPUs and home cluster. So, bottom line, somebody will have to run the schedulers. Definitely, you don't want to do this by hand, so you will have to have a list manager that is sitting alongside the scheduling that actually goes to the various sites and does the leasing. And you will have somebody that actually manages it, and more often than not, it's not the final users. You will have essentially a list manager administrator that does the work. Just a small graphics. What happens, right? The list manager sends around requests to the sites, and voila, we get more resources added to our overlay system. You will also hear this called resource provision, because in the end, the list manager is provisioning resources that are then used by the scheduler. Now, as we said, HTC is a useful thing for the resource owners because it allows them to get the most useful computation out of the machines they have bought. So they will likely have their own machines managed as an HTC system too. So in the end, the list manager has to talk with the HTC system. So we have layers of HTC system. Here we have one, and here we have two, and the two have to coexist. And in the end, when we get the list request, it's just yet another HTC job. So the list manager itself becomes a user of HTC systems. So the lease request, which is a job, it's usually called a pilot job. And the reason being is that it is not running the final user job, but it's somebody that comes in, leases the resources, and then attaches it to the high-level scheduler, the overlay system, and somehow manages which user will actually use the resources for the scientific computation. One thing that you have to understand, though, is because it is an HTC job, the pilot it's a job itself. It has to behave like a job itself. And now I don't know if Tim stressed it yesterday or not, jobs in an HTC system are expected to have a relatively short lifetime, because that's the only way you can manage hundreds of thousands of users and not get starvation for some of them. So, since the pilot job is a job, the leases are relatively short. So, when you create an overlay system, it will be, by necessity, very dynamic. So, the leases will come and will have to go within a reasonable amount of time. And this is usually in the order phase. And the user jobs really have to fit exactly in that as well. It's not a big deal, but something to keep in mind.
Will this limit dynamic or statically managed by the administrator?
It's usually dynamically.
Dynamically?
Yeah. It can be well, it depends which part you say. The policies are usually set are sort of static. They are set by the administrator and changed rarely. They are still dynamic, but they can be changed. But the jobs themselves are very dynamic. The list manager continuously should do it. Although it depends on the implementation. There are many implementations of the overlay systems. We will concentrate today on something called Gliding WMS, because it's what we use in OSG. But that's definitely not the only one. Here are a couple examples, not claiming it's a complete list, just a few I know. There is Panda, Dirac, Alien, Cycle Cloud. Just a few of the possible implementations that are out there. The Gliding WMS is based on HT Condor, which is nice because you learned about Condor yesterday. So nothing really new to learn here. And definitely the most used in OSG. So this is why we go for it. So, just a picture of what Gliding WMS is. We'll not go really in much details about how Gliding WMS work. If you're interested, I have a set of slides that are for administrators of Gliding WMS. I had a whole week about that, so definitely don't have the time today to go over it. But from a high-level point of view, from the user point of view, it just seems the regular Condor code. You have seen this yesterday, right? You have the scheduler, you see the central manager, but you have no dedicated worker nodes. The Gliding WMS services on the side are really the list manager. What we have seen before called the list manager, replacing the Gliding WMS, you get exactly what a Gliding WMS instance looks like. And this Gliding WMS instance goes and submits jobs that will list the resources that will get attached to this. I think I have an animation here. I think that's on this one. So you have heard me that I do something called gliding factories. Well, a gliding, it's really just a HT Condor pilot. And all it does, it really starts schedule node on a list resource. So when the user submits a job, the Gliding WMS notices that it has no place to run this job, so it will submit a gliding to a site's scheduler. Eventually, the gliding will be scheduled, and it will get hold of the resource, it will lease this node, and start the start unit. Once the start starts up, it talks back to the collector, the usual magic happens, and the job starts. So this is how the whole overlay system works. Of course, it happens at larger scales. It's not so synchronous. You will have hopefully thousands of start lists there on tens, if not hundreds of different sites. But conceptually, this is always going on. Nothing complicated, very simple, conceptually, very easy. One thing that you have to keep in mind once you start using the Gliding WMS is that you really have two levels of matchmaking. Yesterday, remember the requirements. You submit a job and you specify the requirement where you want the jobs to run to. If you specified it wrong, your jobs will fail, or they will never start because you ask for something that doesn't exist. It's similar here, but you have really two different layers. One, you have the list manager that has to go out and find the resources for you if they're not available yet. And once the start list starts up, it must match whatever it has found them with your job. Now, the two matchmaking expressions may be slightly different because at the time of leasing a machine, I may not know exactly what I will get. As a trivial example, your job may need, let's say, 2 gigs of memory, or it will not run. A site is providing resources that are anywhere between half a gig and 4 gigs. And there is no way for the list manager to pick one. You just can ask for one. So if you ask for 2 gigs of memory, well, the list manager has two options. Either doesn't consider that site at all, or it takes chances and asks for a machine anyhow, and if it gets a good one, it will get your job matched there. If it doesn't, well, it will ask another one until it gets one. Just a trivial example. I'm not saying it's a realistic one, but just to understand why we have two different. So this makes the system slightly more complicated. So the way it is done in the gliding WMS, we will be using gliding WMS, is that we get rid of the requirements from the jobs, and instead just define, ask the users to define the attributes, and the policies themselves are implemented by the gliding WMS administrators. They will write the policies in such a way that they are compatible between what is requested by the gliding WMS sites and what actually ends up being a requirement in the startee. Remember, both the startee and your job have requirements, and they can be written either way. So we say no requirements in the job or requirements in the startee. You still get exactly the same behavior. It's a little bit less flexible, but it allows us to get what we want. In our case, in the exercise, we'll mostly look at the desired sites. So you specify where you want to run, let's say UCLD, Wisconsin, and so on, and the system will make sure that your jobs end up only on those sites, if you really ask about that. You don't need to put anything in your requirements. And if you do a counter queue, you will say that your requirements just say true, basically. But the thing still works because the startee itself has a requirement that will import it. As I said, this makes the matchmaking less flexible because you cannot write arbitrary expressions. You can only define whatever the system policy is. But on the other side, it's much easier to use. You don't have to think about the Boolean logic. You just define a few attributes and everything gets happened automatically for you. But it also means that you need to know what the system policy is of the system that you run on. And if you go to two different WMS installations, you may get two different policies, so you may need to use two different set of attributes to define what you want. That's just how the implementation works. And this is all I have for the lecture.